with Bankura Christian College, Department of Physics. And I thank Dr. Mondol and Dr. Chakraborty for the nice introduction, kind introduction. And it has been only for my longtime friend, Dr. Karavdar, who invited me. And I cannot say no to him because he taught me a lot of physics when we were in science college. So it's a good opportunity for me to get back to the students, and I consider myself as a student too. I cannot give you a detail, but I will take you step by step through the applications of nanoscience, and the subject I will deal with is nanotheranostics from cell to tumor. So the word nanotheranostics may be a little bit new to you, or maybe some of you know. So it is an agent. It's some chemical, okay, some material that can work as a drug, can work as a therapeutic agent, can work as an image contrast. So it's kind of all in one. So it's not only medicine, it's not only an imaging agent, it's everything. So we would see how this nanotheranostics can help us in developing the current status of medicine that we have today, from cell to tumor. So that means what I'm talking about is the cell is about 5 to 10 microns big, and the tumor can be millimeters to centimeters. So from that scale, I would like to address this problem. So the basic thing is the detection of the disease. The detection of the disease normally is not very easy because we are reluctant to go to the hospitals unless we have a problem. And this is the reason why the time we go to the hospital, and let us say that we are thinking of cancer in our mind because that's the most deadly thing. So by the time we are in the hospital because of any problem, we are already in the stage 3 or stage 4 type. That means the tumor has already started or it has developed. However, our goal is to take this stage much earlier, even before the tumor has started. So let's say in time, in the scale of time, we are thinking of time 0, when there is just a polyp. But polyp is again a tumor which may be benign or malignant. But if that is time 0, ideally we would like to take this detection to even to a negative scale. That means when there is no polyp. Now the question is, if there is no polyp, then how can we detect any disease? So for example, if you are anywhere in the West, the people, the normal population, they will check their body every year. So even if they don't have a problem, in that case, what do they check? They are not looking for a tumor. They are looking for any abnormality which may be there in their body fluid, in their blood, in their serum, or wherever. But if you are looking at that part, then probably you are trying to have some molecular level sensitivity, because there is nothing to image. There is no mass. There is no tumor that has already happened. So you are looking for some very small change in the physiological fluid, in your saliva, in your blood, or wherever. So that is our goal, that we will, if we can take the level of detection to a negative scale, then our chances of treating the disease, whatever disease it may be, is much higher. Okay? And when the tumor has already started, let's say, so we have a tumor, then we have different modalities of imaging that can image it. For example, in this image, you can see there is a mammogram, it's an ultrasound, and MRI, all imaging the same breast tumor. Okay, and you will see that some of them have better resolution, some of them have better contrast. So the information coming from all these techniques, ultrasound, MRI, or mammogram, they are different. And we need to find out the best technique that is required to image. So when you are thinking of molecular level sensitivity, you are not looking at a tumor, you are looking at body fluids. And when the tumor has already started, then actually you are looking at some imaging technique. So we will see what Nano can do in these areas. So after we know this, that okay, we have molecular level sensitivity, or we can image even a small tumor, let's say level stage 1 or stage 2. And then our job is to deliver the drug okay, and make the drug reach the active site, where the disease site, and then we will do some kind of therapy. Okay, so there are four things to do. Basically, you sense if it's a molecular sensitivity, molecular level sensitivity and specific, that's very good. Then we need to image, so we know the size and the location of the disease. Then we send in the nanotherapeutics, so we need some kind of delivery, because we don't want to take the drug like a conventional drug, that okay, I have a headache, so let me take a 650 mg of Calpol and let's solve the problem. It is not that kind of trouble. So we are thinking of delivering very, very minute amounts of therapeutics, very tiny amounts of milligram, nanogram, microgram amount of therapeutics, and take it to the disease site. Okay, so that's a delivery issue, number three. And the last thing is therapy. I can do the therapy using a drug. I can do the therapy using some other technique, maybe heat. I can also treat some disease with heat. So these are the things that we are going to discuss. And in all of these, you can see there are subgroups. So for example, therapy, you can think of efficient therapy, triggered therapy, and when you take some drug, how good it is for clearance. You don't want your drug to stay in your body for a long, long time. That might have other toxic effects. So we would like to address all these things in this webinar. So we know that we have normal cell, we have cancerous cell, and they are different in their structure. For example, on the left, this is your normal cell, and on the right, you have the cancerous cell. You can see they are different in structure. And even when you, this is an animation, not a real picture, but you can understand that a cancer cell is basically, in very simple word, a cell which has forgotten to die. So that means the apoptosis, the automatic cell death mechanism, is not there anymore. So that cell will continue to multiply and grow until it makes a tumor, and then that's a bad thing. Okay? So if you want to look at these normal cells and cancer cells, not in the tumor level, as I said, that I want to look at it from the cellular level. So changes should be at the molecular level. Then how can we see that? I cannot image, for example. So if you see imaging cells versus tumor, when you look at cells, then the cells are very small, 5 to 10 microns. So unless you have a microscope, you cannot see them. However, the imaging techniques that we have for tumors, for example, MRI, CT, or SPECT, or PET, all these kinds, these are for big size objects, like you have a tumor millimeter, centimeter size, then it's fine. However, the cells are micron size, so mostly we use fluorescence. For example, in this image, you can see all these red, green, blue, these colors are coming because we have stained the cell with some dye. We have stained, so that you can see the blue, nucleus is blue, and the microtubules are green, and something is red. So we have stained, and we have taken a picture under a microscope, so we can see how the cell look like. So if there is any change between a normal cell and a cancerous cell, I should be able to see it, but this is only fluorescence imaging. However, currently, a group in South Carolina in USA, they have started doing MRI of cells. But look at this picture on the left. This is a fluorescence image. So you can clearly see the cells, which are green in color. However, this is a 7 Tesla MRI image where the cells are appearing like a dot, black dot. This is because our spatial resolution is not that much in MRI. So that's why a 10 micron or a 20 micron cell is looking like a dot. However, using a microscope, I can see them. So this is the trouble, that what can I do if I want to have molecular level sensitivity or sensitivity sub-micron range? When the cell is, lower than a micron, then how can I see what kind of problems it is starting? Because even before a tumor starts, basically the trouble starts in the cellular level. So if you can see that, then it's possible that we can stop the formation of the tumor itself. So now, straight away, I come to this idea of nanotheranostics. And I want to tell you that what this material is. So you have to basically think of a material, okay? And it has multifunctional properties, many functions of the same material. So for example, I have a material which is nanoscopic in size, that means between 5 and 100 nanometer in size. And that material can be solid or hollow. It can be solid or hollow, but never mind, whatever it can be. I have to put a medicine with it, so there is a drug payload. So there is a drug. I can put the drug inside, or I can also put the drug outside by some chemistry. So many of you, I mean, the physics students are also very good in chemistry. So you can do the chemistry, and you can have this nanoparticle connected with a drug, okay, by chemical bonding or something. Then, because it's a theranostic thing, so I not only drug, I want to do several kinds of imaging also. So for imaging, you need to have some contrast agent. Otherwise, you cannot see. So, for example, you can put a radionuclide. Radionuclide basically means a radioactive isotope. You can put that isotope with the nanomaterial, and then you can do PET or SPECT imaging. Okay? SPECT is single photon emission computed tomography. That is SPECT. Okay? Now you are thinking that, okay, how can I do fluorescence imaging? Okay, for fluorescence imaging, you have to put in some kind of fluorescence molecule or dye with the nanoparticle, which is over here. So if you attach the fluorescence molecule and then you send this nanoparticle inside the body, and if you can make them go to the tumor, then you can shine light from outside, and using a microscope, you can take the image. Okay, then likewise, you can put some material which is X-ray active. So for example, you can photography. You can do X-ray CT. So the final problem is, okay, now I know a material, a very small material, which is nanoscopic. It can contain drug. So I can release the drug when this nanoparticle reaches my disease site. But the question is how it will go to the disease site. If I drink it with water, then it will go throughout my body. Then what is the guarantee that it will reach the tumor or it will reach the disease site? Okay, for that we need something called a targeting agent, which is this blue circle over here. A targeting agent. What is this targeting agent? It's again a question of knowledge of chemistry and biology. So for example, a targeting agent can be an antibody. A targeting agent can be some kind of particular chemical. Normally in our biology language we say receptors. Okay, so receptor is basically our cells have a certain receptor. It has many receptors, and we will make something on the nanoparticle that identifies this receptor, and they are like enzymes. For example, they have a lock and key action, so complementary to each other. So for example, if you have some idea of DNA, you know that we have the 4 nucleotides. Okay, A, T, G, and C. A and T are complementary, G and C are complementary. So something like that. So one we will put on the nanoparticle, the other we will put on the, we know that they are on the cell. So if I send this nanoparticle, the nanoparticle will look for some complementary molecules on the cell. Wherever it finds that complementary molecule, it will go and bind. And this knowledge we have. We know what kind of cancers have what kind of receptors. Accordingly, we will prepare the targeting agent. So once we have this, now our job is pretty much simple. So I need a carrier. So the question is what kind of carrier? Okay. And I need targeting. Okay. So I know that if it's a breast cancer, if it's a cervical cancer, it is some skin cancer, melanoma. So I know what kind of chemistry I need to do on the nanoparticle. Fine. So that's a targeting issue. Then functional loading. Functional loading means I need to put a drug, because when this nanoparticle reaches the disease site, I need to release the drug, and then the drug will fight against the cancer. Okay, so there must be a drug. Okay, so for example, normal chemotherapeutic drugs are cisplatin, okay, doxorubicin, this kind of drugs are used. So that's my functional loading. The other functional loading is what do you want to do with the nanoparticle? Do you want to do imaging? If imaging, what kind of imaging? MRI, CT? Accordingly, I need to put some other molecules onto my nanoparticle. Okay? So together, they make the whole nanotheranostic design. Okay, it is not very simple. Yeah, it needs a lot of designing, material designing. Let's see how it goes. So the tools that we have with us is a material. So the first thing we are thinking about is a material, of course, in the nanoscopic size, which can be inorganic or organic or a hybrid. Inorganic means you can have semiconductors, metals, gold, silver, silicon, this kind of materials. Organic means most of the hydrocarbons you have, and hybrid means it's a mixture of inorganic, organic. And function, so you are thinking of the function. So am I going to do sensing, or am I going to do imaging, therapy, or drug delivery, or all? So that's the question. And if I want to do imaging or if I want to do therapy, then what is the technique? So for example, you want to do imaging by fluorescence or sensing by fluorescence or Raman spectroscopy. Okay, amperometry, that means you are measuring current, voltammetry, you are measuring voltage. If you want to do imaging, then the question is, am I doing fluorescence or IR, infrared, or thermal camera? You know, normally nowadays, if you travel somewhere, then people are coming to measure your body temperature. They use a IR gun to measure your body temperature, and that is like thermal imaging. So this IR camera that normally, you know, you go to the airport or somewhere, they're measuring your temperature. So that's the IR camera. You can do MRI, X-ray, CT. So the question is what you would like to do with your material. If you want to do CT, then in the material, you have to put some material which is CT active. Similarly, photothermal therapy, we are looking at therapy. So what kind of therapy we want to do? Chemotherapy. If chemotherapy, then doxorubicin, okay, cisplatin, whatever drugs are known drugs are there, we have to load it into our nanoparticle. Okay. If you want to do therapy like say photothermal means you shine light, photons, you shine light, and that light will convert to heat, and that heat can kill a cell. Heat can be used to kill a cell. Then there is a treatment called photodynamic therapy, which I will not discuss, but there are ways of these therapies, or combinatorial, that means a mixture of all. So you have some heat, you have some chemo, you have some dynamic, everything together. And of course you need targeting. Without targeting, nano is useless, because the main objective of using nano is to reduce the level of the drug. So you don't want to take that 650 mg of Calpol when maybe only 1 mg is required. And that is because when you take 650, the other 649 mg is lost in your immune system. Only probably 1 mg is working. But because it is non-targeted, the Calpol is non-targeted, the paracetamol is non-targeted. That means, you know, you have to take more because your immune system will degrade most of the drug. So only a little bit will reach the disease site. But in nano, what we are doing is we are hiding the drug inside a box. Our nanomaterial is the box. So we hide it so that the immune system cannot degrade the drug inside. And when it reaches the disease site, which may be a tumor or whatever, then I open the box. When I open the box, the drug is released. That's why I need very little amount of the drug. Okay, in simple words. Let's see what we can do. I make a nanoparticle, then I have to make it so delicious to the cell that the cells like to eat it. If not, then I cannot do anything. The first job is to make a nanoparticle go inside the cell. Then I will look whether I can kill it or not. Okay, there will be different parameters that affect the nanoparticle uptake. For example, size. So a cell is 10 micron, let's say. So which size do you think that it will be easy for the cell, for the nanoparticle to go inside? Of course, the small ones. But if you take too small, less than 6 nanometer, let's say, then most of the nanoparticles will go out through the kidney, renal clearance. Okay. If you take very big, then for example, it will not enter the cell. So there is an optimum size. Okay. Now the material can be inorganic, organic, or hybrid. Okay. So it can be metal, it can be semiconductor, it can be carbon, it can be polymer, it can be a liposome. Material dependent, shape dependent. Okay, it can be a sphere, it can be a cube, it can be a rod. So all kinds of shapes you see here. So some of them are easy to go in, some of them are difficult. So just to give you the idea, think intuitively. If it's a tiny Spherical particle is very easy to go in. But if you take a star, for example, which many spikes, it is difficult to penetrate the cell membrane and go inside. So similarly, you think of the surface charge. Now look over here. The nanoparticle may have a surface charge, which is positive, negative, or neutral. So the surface charge can also facilitate nanoparticle uptake. So these are the parameters that will affect the uptake. So first we have to understand that how to design these nanoparticles so that they go inside the cell. Okay. Now let's start with the material. Okay. Organic, inorganic, and hybrid. Among the organic group, what you have are dendrimers, micelles, liposomes, and hydrogels. What are they? They are very simple. Look at the figure, they are very simple stuff. So for example, liposome. Liposome is nothing but the phospholipid, the bilayer lipid that you have on the cell surface. All of our cells, on the outside, we have a cell membrane kind of thing. And that membrane is made up of this lipid. So liposome is a hollow structure made up of the lipids. So inside is hollow. So you see this red part, this core part. Now I am coloring it red. So that's hollow. So it's a nanoparticle which is very small. Outside is a liposome, that is a bilayer of lipid. Inside you can put your drug. Inside you can put anything. And then these nanoparticles are very small. Okay, 5 nanometers, 6 nanometers. So you can send them in the bloodstream and let them go to the disease site. Similarly, you have micelles. Now these are polymeric micelles. We call them micelle, but they are made up of a polymer. And inside, again, it is hollow. You can attach the drug from outside also. We can do the chemistry, but it is easier to put it up inside. Then can protect the drug from our immune system. Okay, so I can load the drug over here. So here is my drug. So similarly, you have other kind of structure. Hydrogel is basically a gel-like substance made up like a water bubble, Inorganic, in the inorganic comes the semiconductors and the metals mostly. So you have gold. So gold nanoparticle, gold nanorod, gold nanoshell, gold nano cage, all these kind of structures. And of course, you have the quantum dots, which is a very promising semiconductor material that emits very bright light. Okay, it's a fluorophore. So you can have very tiny particles of gallium arsenide, gallium nitride, indium arsenide, indium phosphide. They emit light. Once you know they emit light, you immediately know they can be used for bioimaging. That means I can put these quantum dots inside our blood and make it go for how big is it, where it is. I can do everything. And of course, then you can have a combination, hybrid. So you can have, for example, in this picture, this may be a gold nanoparticle with a liposome. Or you can have a metal nanoparticle inside a hydrogen. Or you can have some mesoporous silica. Mesoporous silica is very interesting. This is mesoporous silica inside a micelle. Mesoporous silica means you have silicon dioxide, SiO2, which has many holes. It's porous. And immediately you understand now why it is porous. Okay, it is porous because I can load drug inside. That's why it is interesting. So the outside silica, SiO2, is very stable. It's oxide, so it is very stable. I put some drugs inside. That is silica box. That box will protect the drugs inside. And then you carry the mesoporous silica in your bloodstream and take it to the tumor and then release the drug. So you have to make a wise choice which one of the material, organic, inorganic, or hybrid, you have to use. Okay. Now, organic is the best choice. For example, if it is organic, you know our body will not reject it because our body likes organic stuff. Because we immediately realize, our immune system realizes if something is outside the body. So if you take something organic, for example, the liposome, which is exactly mimicking our cell structure, then our immune system cannot detect it. Because if the immune system can detect that, okay, this guy is a foreign substance, the immune system will send its fighter bombers to kill it. Okay? So you don't need that because that's your catch. I have my drug hidden inside. I cannot allow my immune system to destroy it. If it is destroyed, then I lose my drug. So that's a step. Okay, I have to hide it inside the box. So here is my drug, let's say paclitaxel, which is also anti-cancer. So I hide it inside the liposome, and then I can functionalize. For example, I can have a targeting ligand. When I know the targeting ligand, if I can do the chemistry properly, I know this liposome is going to which kind of cell, whether it is going to a breast cancer cell or a lung cancer cell, I know from the targeting agent. Okay, then I can put some imaging agents, MRI, CT, whatever. I can put some chemicals on the surface, so it will become MRI active or CT active, fluorescence active. I can put targeting agent. Now the other thing is I have to make this nanoparticle delicious to the cell. So sometimes I use a coating of PEG. I use a coating of PEG. PEG is nothing but polyethylene glycol. So polyethylene glycol, if you coat the nanoparticle with this material, most of the cell, it is like, sweets to the Bengalis. So they like to eat it. The cells like to eat that up. So they eat it, and then we start our magic. So this is how you can design a nanoparticle. So this one is for liposome. You can do exactly the same stuff with micelles, polymeric micelles. What kind of polymers, you may ask me. So polylactic acid, polyglycolic acid, and whatever these are can be, and you use it in exactly the same way that you used the liposome. Okay, so but these are organic, so it will be very safe for you to use. Otherwise, the FDA, the Federal Drug Authorities, they will stop the nanoparticle. They will not give the approval. So that means you cannot use it. Now let me discuss a little bit about targeting. Targeting, basically there are two types. One is called active targeting, and which is the best. The next one I am going to show you is automatic. It is not really very good, but okay, it still can work. So that will be called passive targeting. So let's start with active targeting. So for active targeting, what we have is, we have a nanoparticle
significant role in some energy sector, for example, here. So piezoelectricity, you see, 1880 it was discovered, as I mentioned, and one of the classic example that every day we use is the gas lighter in the kitchen, right? You give a force there, you can see some sound like tack, and then it get fire because it's come close to the LPG. What happened? There is a starter, there is electrodes, there is air, and there is a piezoelectric crystal. So once you hammer it, and it's giving a lot of potential, kilovolt kind of order, and so air basically getting ionized. So that ionized air, when it's coming in front of the LPG, and you are getting the spark. So that is the basically, you can imagine how how much utility of this particular small device, but every day we are using. So it has enormous impact actually. There are many other sectors that I'm not touching, but this is the example that everybody we are using this lighter actually, and you can imagine the small gentle pressure can give rise that much potential. So it has other applications that you can think of. So, and then why basically this nano stuff coming into the picture? The question comes, right? So what happened in 2006? Professor Zedel Wang, he is again another physicist, and he's basically Georgia Institute of Technology. And what he did, he made a zinc oxide nanorods, and this is zinc oxide. You see, once you give a pressure, and there is a polarization, displacement of the ion, and non-centrosymmetry things, basically symmetry is breaking here, and there is some polarity. So what is his idea? His idea was to measure the Young modulus of zinc oxide nanorod, and then you can we can connect with your practical room, Young modulus, the bending of the beam, and we calculate the Young modulus. We put a load, and then we calculate the displacement and nice curve, and we take the slope, right? So, and you imagine once you have a nanomaterials like nanorod zinc oxide, the length is maybe 500 nanometer and diameter maybe like 10 to 20 nanometer. Then how can you measure the Young modulus? So that's still is challenging. So then Professor Wang, he had some idea to how to measure it, and there is a technique known as AFM or scanning probe based techniques. So what happened? There is a probe, and the laser is falling in the tip, and it is scanning through the zinc oxide nanorods. And you see there is a path here, and as it progresses, and once it reaches different places, you may see different deflection, right? Because it's passing through the different region. So if you ride a bicycle, right, and there is a bumper, whenever you find a bumper, then you get safe, right? So it is like that basically, but in the nanoscale and then that displacement we measure, and then he observed whenever it passing through the zinc oxide nanorock, he found there is a voltage and current spike here, and then he discovered that there is a piezoelectricity is happening here in 2006, very close, right? So he gave the name of piezoelectric nanogenerator, and it was published in Science magazine, a very famous magazine. So that's the basically invention of nano generator.